Okay, so just to review the quadratic formula, A is 2, B is 4, and C is 1. So the opposite of B, plus or minus, the square root of B squared, and this is always going to be a positive number because you've squared something, minus 4 times A times C, all over 2 times A. What would I have under the radical? -16 minus 8, right? So if I break 8 down, how does that simplify?
2 square roots of 4.
2 square roots of 2. 2 square roots of 2. Because 8 is 4 times 2, and so that's 2 root 2. Now when these numbers here, here, and here are reducible, and we reduce them. I didn't highlight the one under the radical, okay? So I would divide all these by 2. My answer would be -2 plus or minus 1 square root of 2 over 2. That's my 2 answers. We could type in, get 2 different decimal approximations. Now, that's not factorable, because I don't think that you guys would be factoring this problem right here. And you'd say, oh, okay, yeah, that would be x minus 2 plus the square root of 2 over 2, and x minus, actually minus a negative 2 minus the square root of 2 over 2. Now, who thinks of those numbers off the top of their head? Nobody. And so we don't really, I know just 1 or 2 of y'all do, but really, that's why it's not factorable. That's why we call this prime. Now prime, let me clear this up. Prime only works when you're factoring. That's the only time you can throw that in there is when you're factoring. That just means it's not factorable. But as you see with the quadratic formula, it does have a solution. All right, just to review a little bit about completing the square. Alright, first step in completing the square, take my constant to the other side, make my leading coefficient 1, so that would be 1x squared plus 2x equal -1/2. So I've got my constant to the other side, I've got my leading coefficient is 1, I'll take half of the middle term and square that, and add it to both sides. I purposely made this a perfect square trinomial to factor it into a binomial squared. What do you square to get this? The middle sign. And what did I square here? I squared 1. And then I combine like terms there. And then to get rid of a square, I take the square root of both sides. Now the square and the square root, what do? Cancel out. Undo each other. So x plus 1 is equal to plus or minus the square root of 1, which is 1, over the square root of 2. And when you see that, hopefully you remember, wait, I've got to rationalize that denominator. I can't have a radical in the denominator. So I would multiply top and bottom by the square root of 2. And that would leave me the square root of 2 over the square root of 4, which is 2. Then I subtract this 1 from both sides, and that would be -1 plus or minus the square root of 2 over 2. And that's the same thing as here. Can somebody explain to me how those are the same? Where's the 1 come from?
You divide the top 2 by the bottom 2.
Yeah, these share a denominator of 2. So -2 over 2 is -1, and the square root of 2 over of 2 is here. So those are equivalent to each other. Factoring method wouldn't work, but completing the square and quadratic formula will work on all of them. Now, I understand why you guys couldn't do a few of those with eyes in them, because we just have started talking about those today, but you'll get there. We'll be able to complete those. All right, would you do the quadratic formula with this? Just trying it. So far, so good. That makes great if that were just an 8 and we could break that down. 4 times 2, get 2 square roots of 2. But this negative causes us a problem because if you take a square root of a negative on your calculator, does it say domain error or just error or I don't know what all they say. But that's because our calculators don't deal with complex numbers, and that's the type of solution. I'm going to call a timeout right there. And then we're going to look right here, okay? We're talking about the imaginary unit today. I is a number, and it's equal to the square root of -1. Some famous mathematicians, Euler, which spells his name, and that's that Italian guy, I can't think of his name, Cardano, or that's not it. Anyway, they decided that it made no sense that you had quadratic equations that had no solution, that they had to have some type of solution. Yes?
This was on ICT.
Yes. Was it? Great. Bad timing. All right. So, they came up with, and what's interesting, there no internet, couldn't communicate, but in different parts, different places, they thought this doesn't make sense, and so they decided that there had to be another number system, and there is the complex number system, and I is equal to the square root of 1. Now there's a pattern with i's, and I'm going to show them to you. If I squared both sides, what would the square do right here?
Square the negative
What?
1.
That would do what?
It would square the negative 1.
What would the square root and the square do?
It would
Cancel out. And so I squared would just be equal to -1, which is a real number, isn't it? So I squared, so anytime you see I squared somewhere, make it a -1. Simplify it. It's a real number. Now, if I multiplied I squared times I would get I to the 3rd. If I multiplied I times I squared, I'd have -1 times the square root of -1, which would be -I. Because what's the square root of -1 equal? I. So back to complex numbers. This is not real, is it? It's not a real number. No, listen. It's a real number, and it exists. Okay? But when the book says it's not real, it's talking about not a real number. Make sense? It's not like the tooth fairy. It actually does exist, okay, but we just call it imaginary numbers, okay? All right, so if I multiply I to the 3rd times I to the 1st, I get an I to the 4th. Well, what would I get if I multiplied -I times I? -I squared. What's I squared? -1. What's -1 times -1? +1. So any even power is a perfect square. Any even power is a perfect square. So I think I'll just let you write those things down real quick. And you've got the whole pattern, because once you get back to I to the 5th, you start right back up here again. I to the 5th is equal to I, because 1 times the square root of -1 would be equal to I. I know that's confusing. Give us a few minutes and let's work some problems, and I think you'll be fine. So copy down those 4. Okay, so this is the pattern that repeats, and if I go back to I to the 5th, let's say, I to the 5th, that would be the same thing as I to the 4th times I. Well, what's I to the 4th? 1 times I would be I, wouldn't it? All right, so what would be I to the 32nd? Well, this is a multiple of 4, and so I to the 32nd would be 1. You can't do this on a calculator. So what would I to to the 14th be? Okay, what's the closest multiple of 4 to 14?
16.
Let's say I said 12. I'll go to 16 in a minute. Let's say I said 12. 12 would be right here. Out of the 12th would be here. So then 13, 14. So out of the 14th is -1. Okay? All right, let's go like he said 16. 16 is a multiple of 4. That would be here, right? So 16, 15, 14. I still get back to here. It's just a repeating pattern. And so what would I to the 21st be? What's the closest multiple of 4? 20. So 21 would be back equal to I. So it's just a pattern of 4. You just go through there and think about what would be the closest multiple of 4 to get there. All right, all that being said, just defining what I is. Do y'all get that? All right. Pi, which is what kind of number?
Irrational.
Irrational, is talking to I, which is not real. It's a joke. Y'all can fake laugh now, but I understood. It's pretty funny. All right. Here is the number system with now the real number system with now the complex system hooked onto it. You notice that before today that you've always just dealt with the real numbers, and they were a system divided into rational and irrational, and then inside the rationals there were integers, wholes, and naturals. But if you'll notice, the real box is now sitting in this complex number box, and over here by itself is just a pure imaginary part with just i's in it. Both the real numbers and the pure imaginary numbers are called complex numbers. Complex numbers are written in this form. I like the way you guys are just sitting there with nothing to write down. This is all new stuff. I appreciate that. But anyway, I would write it down if I were you. I plus BI stands for the standard form for a complex number. And the A part is real, and the BI part is imaginary. Spell. Imaginary. Now, you say, okay, the real numbers are complex, right? The real numbers are complex. The pure imaginary numbers are complex. And all of them can be written in this form. So let's say we're talking to the kindergarten who's just barely learned to count from 1 to 20. Yeah. And we talk to them about writing their numbers in complex form. Wouldn't that be fun? Because you say, okay, here's an example of 7. You'd say 7 plus 0i because the imaginary part is 0. That'd be great for a kindergartner, wouldn't it? Blow their little brain. It's blowing yours right now, right? But with real numbers that have no imaginary parts, which are all the numbers you've heard of till today, isn't it cool if there's a whole other set of numbers out there you didn't know about? I think that's cool. But anyway, every number that you heard of till today, its imaginary part was 0. Do what?
It's already bad at the first set. They're already bad at the first set.
I'm adding no more. It's crazy. All right. So its imaginary part is 0. So all the real numbers over here, even the fractions and decimals, their real part's here. Their imaginary part's 0. And then there are numbers that have no real parts. They're just imaginary. They just have i's in them. And so 2i, I could actually write like that where its real part 0. So then there are numbers that exist that have both parts. And they look like these. Have a real part and an imaginary part. A real part and an imaginary part. And again, I said, said, if we were dealing in electricity, talking about vectors, we'd have apply this. But for right now, we're going to talk about them as solutions to quadratic equations. And then what's above quadratic? Cubic, quartic, quintic, all those higher powers of polynomials. And when you get into pre-calc, you're talking about P's and Q's and figuring out what the solutions could be to all those polynomials. That's where you're headed. And I think I told you the other day, there won't be many days that go by in pre-calc when you're not factoring. And when you run up on one that's not factorable, what are you going to be able to pull out of your pocket? The quadratic formula. Because hopefully you put it in your pocket, right? You don't forget about it. Now, completing the square, if you're feeling like you want to punish yourself for something you did, you can complete the square. You will use completing the square when you put things in vertex form to be able to graph them and all that kind of stuff. You do need to know how to use the completing the square method, but what we're finding right now are just solutions. And not all the solutions are real numbers. Some are complex. Think about the graph of a polynomial that's just real curvy, that hits that x-axis several times. Might have all real solutions. Some of them are way up above the x-axis doing stuff. Well, all their solutions are complex. Some of them may hit the x-axis a couple of times and then not again, but it's higher than a quadratic. That means it has some real and some complex. So that's where you're headed with all this stuff. Does anybody have a question about just a whole new set of numbers? What is I? The square root of -1. That's right. The square root of -1. So I has just become a number like pi. Pi's a number, right? It's an irrational number. Now I'm telling you I is a number and it's imaginary. E is also a number. Euler made up his own number. I call it Euler's number. That's cool, isn't it? If you made up a number, would you name it after yourself? Absolutely. So, Euler's number we can deal with in exponential equations. But right now, new set of numbers, complex numbers. Anybody have a question so far? Let's apply this. Let's go backward to this problem that Daniel was working earlier. I'm going to finish it out for him. -8 breaks down to -1, and then the 8 breaks down to 4 times 2. Now the square root of -1 is I, and the square root of 4 is 2. So that's 2I, and then this 2's got to stay in the house, got to stay underneath. That's the real solution. But now remember, when these 4 numbers are reducible, what do? We reduce them. Whoops. So in simplest form, if I reduce everything by 2, that's the actual answer to that problem. That would still be a parabola if I graphed it. It would not have any x-intercepts because it has no real solutions. But, like Euler and Cardano said, it's got to have some solution. And here it is. You say, well, I thought you could write that in this form. It's a complex number. We will. Let me split that up with a common denominator. And then let's reduce what we can reduce. So it's A plus BI. A is -1. That's the real part. On this side is the imaginary part. And B is the number with I. What's the number with I? Square root of 2 over 2. So that problem you were working had solutions. but they had imaginary parts. Don't try to figure it out, just accept it. I is a number. I is equal to the square root of -1. So you guys saw this yesterday? Think you saw some I's yesterday?
Yeah, I missed them.
Missed them?
I just changed my negatives to positive.
Unless I got.
Okay.
That's what I do.
That works sometimes, I guess. Probably not. All right, so let's talk about graphs now. This problem right here could have been a perfect square trinomial, could have been totally factorable, had one, looks like 3 was its x-intercept. It could also be an irrational number somewhere. But this has 2 x-intercepts. It could be factorable, they could both be rational, or they could be irrational, like, square root of 17 or something, and wouldn't have been factorable. We could have found it using the quadratic formula. Now these two are not touching the x-axis at all. That means there are no real solutions. So now we know what kind of solutions do they have. Complex. They do have solutions. They just have i's in them. They're complex numbers. All right, so let's look at this problem right here. Let's do the quadratic formula. All right, A is 3, B is -7, and C is 5. So let's substitute into the quadratic formula. And the opposite of B is 7. And B squared would be 49 minus 4 times A times C. All over 2 times A. What goes under the radical? Y'all got the calculator, right? Huh? -11. Alright, now does 11 break down? No, that's a prime number, right? It doesn't have any perfect square factors. It only has one in itself has factors at all. So, but I cannot leave a negative under a radical. That is just like leaving a square root in the denominator. We don't do that either, right? Do we leave square roots in the denominator? No. What do we do to it to get rid of a square root in the denominator? It's R, right? Huh? Rationalize. All right. So we don't leave negatives under radicals either. This has got a -1 at it. So in it. So the square root of -1 comes out, and the 11 stays underneath, and there you go. I can't leave the negative under the radical. So those problems with quadratic formula that you couldn't do, now you can. Correctly. You can do correctly now. Do it correctly.
So
Yes.
basically the I is just a negative popping out.
The square root of -1. That square root of -11 broke down. And the square root of -1 is I, and then 11 stays underneath.
So no matter what the negative number is, you can just put an I outside and then.
And it takes care of it. Alright, so in complex number form, what's A?
Real number?
What's the real part? 7/6. What's the imaginary part? What's B?
Square root of 11.
Square root of 11/6 is B. Those are ugly numbers, but they're numbers. Alright, so let's look at this problem right here. Let's copy it down. This problem's easy. I'll show you what I mean. They've thrown a variable or two in here. And they've asked us to find X and Y. And here's the point of this problem. If two complex numbers are equal to each other, then the real parts have got to be equal, and the complex or imaginary parts have got to be equal. What's going to happen to those two i's?
Cancel.
So what's y?
-3.
What's x? So the real part's equal to the real part, and the imaginary part's equal to the imaginary part. That's not bad, was it? Very, very simple equations to solve. Do what? That one was, yeah. Alright, I'll give you one to try. The real part's equal to the real part. The imaginary part's equal to the imaginary part. This is an I. Doesn't look very good, but it is.
Something like that.
Alright, so he said 2x equal to negative 8. We found that x was negative 4. And then set 3iy equal to 10i. The I is canceled. So 3y is equal to 10, so y is 10/3. Or 3 1/3.
How do the i's cancel if they're both positive?
When you divide both sides by I, to simplify them, they cancel out. Alright, we can add, subtract, multiply, and divide the new numbers that we've just learned about. Okay? So let's do it. Copy that one down. Consider it as though you're combining like terms. So we're going to combine the real parts and the imaginary parts. And a negative 3 and a positive 7 is a 4. And 5i and negative 6i is negative 1i.
Do that again.
Sure. The real parts, negative 3 and positive 7. 7 minus 3 would be 4. And a positive 5i and a negative 6i, different signs, subtract, take the sign of a bigger term, negative 1i. You can put a 1 here if you need to. So we can add, subtract. Let's subtract. So we'll have negative 3 minus 8i. And then what does subtraction always do? Changes these signs. So that will become a plus 2 and a plus 9i. And again, you put the real parts together and you put the imaginary parts together, combining like terms, and a negative 3 and a positive 2 is a negative 1, and a negative 8i and a positive 9i is a positive 1i.
Broken calculators can do that.
Gotcha. It's a menu or in the,
No, you just have to press second and right there's the
Don't pin on it. Alright, you can multiply them. If you'll notice, complex numbers are written in the form of a binomial. 2 terms, right? What method do you use to multiply 2 binomials? For. So let's do first, outer, inner, last. First would be negative 10. Outer is negative 6i. Inner is negative 5i. And last is negative 3i squared. Alright now, I see some like terms right here. What is I squared? It's -1, isn't it? So this means -3 times -1. So that'll be a 3. A +3 and a -10 make a -7. Say that again. I squared is -1. -1 times -3 makes a +3, which is a real number. And this real number and that real number, if I put them together, give me -7. And then this imaginary part, I just combine those like terms. So I can add, subtract, multiply. Let you try this one. Multiply this one. When you see an I printed in a book or on a test or something, normally they use script. Looks like a little cursive. I don't know, maybe just so it doesn't look like a 1, because some people don't put the dot on there. So that's why I'm trying to do that cursive I. But normally, try not to do a print I, because normally that's not used. But anyway, he is right. Do you guys agree? That's great. Good job. Just learned about a whole new set of numbers today, and we can add, subtract, and multiply them. That's good, isn't it?
What about dividing?
How about dividing?
Oh, shut up.
Yeah, we can divide them.
Everyone knows you
Now,
can't divide.
answer this question. What is I?
Square root of -1.
So you mean to tell me that we have a radical in this denominator?
Rationalize.
We gotta rationalize. All right. So if I have a binomial, how do I rationalize? I use the C word, conjugate. I use the conjugate, which would be 2 plus 3i. So division may be the most fun. It might be the most fun of adding, subtracting, multiplying. I bet division is the most fun. All right, so here we go. Now I've got a binomial times a binomial on the numerator and a binomial times a binomial in the denominator. Do you know why I'm rationalizing this on the bottom? So I don't have a I. I don't have any radicals. If I can't have a square root, I can't have an I, because an I is a square root of -1. All right, so that's why I use the conjugate. All right, here we go. First, outer, inner, last. First, outer, inner, last. And what's I squared again?
-1.
So that would make this what?
-1. No, -15.
-15. That would make this what?
-9.
Plus 9. So 4 minus 15 is -11. Put the i's together. Down here the i's cancel. And 4 plus 9 is 13. There you go. Alright, let me give you some to try.
Hurry up before she does.
15 through 9.
Got a lot to do.
Every other evening to do.
Do this tomorrow.
You want to do these every other odd?
That'd be awesome.
And I'm not sure that you end up on 73 or 77 or 75, okay? It might be around there. It's going to be around there. So every other odd. See y'all tomorrow.